Welcome to Lecture 3.5, Inverse Trigonometric Functions. By now you're probably realizing that similar to in trigonometry in general, where we had lots of identities that you had to remember, we're now hitting this place where we have lots of derivative formulas which you also need to remember. In this course you're not given any formula sheets for any test, so all of the rules around finding the derivative of functions you need to know how to do that, whether it be a process like the chain rule or an actual kind of functional value for like the logs and exponents like we saw before. So today we're going to continue along that, and we're going to look specifically at what are the derivatives of inverse trig functions. So before we start, let's do a quick review of inverses and specifically inverse trig functions. Remember that inverse functions simply undo whatever the original function does. So that's why we say addition and subtraction are inverse functions, because subtraction undoes addition. Also remember, when we're talking in terms of functions, only one-to-one functions have inverse functions. They can have equations can have inverse relationships, but a function by its definition, as far as having the same output for the same input, will only have an inverse function that also meets that definition of a function if it's one-to-one. And again, that's a concept from algebra. And so here with trig, for example, the sine function here is not one-to-one. Remember, we can do a horizontal line test, and if it touches more than one point, then it is not one-to-one. We do a vertical line test to see if something is a function, and obviously the sine is a function, and then we do a horizontal line test, the red line you see there, to see if it's one-to-one. And because this line touches the sine function at more than one spot, we can see that sine is not a one-to-one function. So it doesn't technically have an inverse function. Again, recalling back from algebra, what we would do is limit the domain. So if we only consider the sine function between negative pi over 2 and pi over 2, now we can see that it is indeed a one-to-one function. And this is a very common approach to repeating functions or functions that are not one-to-one, so that we can actually solve some equations and problems. Remember, the notation for inverse functions looks like a negative exponent on the function. We read this as f inverse x equals y, which we could also write as f of y equals x. Okay, so it's the inverse function of f of x is equal to y, and we could also read that same thing as f of y equals x. Remember that we're replacing the variables. So when we're talking about the trig functions, for example, we say inverse sine of x equals y. This means, okay, let's read that again. The inverse sine of x equals y means that if I take the sine of y, that will equal x. The inverse sine of x equals y means that I can rewrite this as the sine of y equals x. And notice I have to limit again the domain in order for it to be a function still. So here we have the inverse sine of x equals y. So I'm just going to prove one of these out, and then I'm going to give you the formulas or shortcuts. So remember that we can rewrite the inverse sine of x as y. We just saw this as sine of y equals x. And so if we want to find what the derivative of this is, notice this is the derivative of the inverse sine of x, we can differentiate both sides with respect to x. So on the left side we get cosine y prime. Remember, when we're differentiating implicitly, we take the derivative, since it's a y variable, with respect to y, and then times it by y prime. The derivative with respect to x of x is simply 1. And then we solve for y prime, and so we see that we get dy dx equals y prime, this is notation, equals 1 over cosine y. Now remember that since cosine y equals 1 minus sine squared y, remember cosine squared plus sine squared equals 1, so cosine y would equal the square root of 1 minus sine squared y. Okay, we only have to consider the positive because of the domain that we're looking at. And remember, we already said that the sine of y is equal to x, so sine squared y would simply equal x squared. And so this is the basic trig function, the Pythagorean trig function. This is using the original equation we got, that sine y equals x, and substituting that in for sine squared y. So we get our ultimate, which is that the derivative of the inverse sine of x equals 1 over the square root of 1 minus x squared. I wish I had put this in inverse sine, because notice it's saying the same thing, that the derivative of the inverse sine of x is equal to the derivative of the sine of y, but basically this is what you want to know, is that it's 1 over the square root of 1 minus x squared. So you can see how we got that. All the other ones could be found similarly for cosine and tangent, and then just reversed. The inverse sine, the derivative of the inverse cosine is negative 1 over the square root of 1 minus x squared. The derivative with respect to x of the inverse tangent of y is 1 over 1 plus x squared. Okay, so notice the cosine version was just the negative of the sine version. Okay, so these are the other three functions: cosecant, secant, and cotangent, giving you the limits on their domains, and also just reminding you of how to write them. And really what you're doing is just switching out the x's and the y's, which hopefully you remember from algebra as well. And so if we switch out the x's and the y's, notice that what happens is now we're just dealing with the cosecant. So y equals the inverse cosecant of x is the same as cosecant y equals x. All right. So here are all of the derivative formulas that you need to know for inverse trig functions. These are not the trig function. Remember, we already did that. For example, cosine equals negative sine. The derivative of sine is cosine, etc. Notice here that you really only have three to remember. That all the cos, the cosine, the cosecant, and the cotangent are negative versions of their cofunction. So for example, the cosine is the negative of the sine function, the cosecant is the negative of the secant function, and the cotangent is the negative of the tangent function. Again, you can see that here. These are the same function with a negative. These are the same function with a negative for cosecant. These are the same function with a negative for the cosecant. These are formulas you need to know. You need to memorize these and practice using them in your homework and other practices. Okay. So just a little review again for trig, just to kind of hopefully prime your pump. Remember that when I'm looking for the secant of negative 1 over 2, or the inverse secant of 2, excuse me, the inverse secant of 2, remember that secant is 1 over cosine. Cosine is adjacent over hypotenuse, so we're looking for hypotenuse over adjacent, hypotenuse over adjacent, hypotenuse over adjacent. So the angle here for number 1 would be 60 degrees, right? Arc sine of 1 over square root of 2. Remember, arc sine is just another way of saying inverse sine. Sine is opposite over hypotenuse, and we have 1 over the square root of 2. So opposite over hypotenuse, 1 over square root of 2. So the angle here is 45, or in radians, pi over 4. The last problem we're going to do, and you've got plenty of practice in your online homework and then also in the lab samples. Here we have the square root of x squared minus 1 times the inverse secant of x. Now this is a little bit more involved because notice we have a product, so we're going to have to use the product rule. So we're going to take the derivative of the first times the second plus the derivative of the second times the first. Okay? So notice the derivative of the square root of x squared minus 1. Again, you think of this radical as a 1/2. So we get 1 over 2 times the square root of x squared minus 1. Okay, times the derivative of what's inside, which would be the 2x. I feel like I'm missing a 2 here. times the other piece there, which is secant negative 1. I do think we're missing a 2 here in this original piece here. Okay? Plus the derivative of the second. Remember that the derivative of inverse secant is 1 over x times x squared minus 1. 1 over x times x squared minus 1 times the other function, which was the square root of x squared minus 1. So the only thing that's wrong here, and I want you to hear this, there should be a 2 down here as well. And so I think that 2 up top will also cancel out. Now why is there a 2 there? Because remember that this is x squared minus 1 to the 1/2. So the derivative is 1/2 x squared minus 1 to the negative 1/2. So there should have been a 2 on the bottom, which should cancel out with the 2 on top. So the final answer should not have this 2 here. Here these factors cancel out, and so we should have x inverse secant x over x square root of x squared minus 1 plus 1 over x. This 2 does not belong there because there should be a 2 down here as well. All right. So try